Okay, so I'm going to do a short tutorial on how to do problem 1. This is from your lab packet, and I'm going to do a different tutorial for each of the problems. So I also uploaded the answer key, so you might get to the point where you can just check your answers and you don't have to listen to the video anymore. So on this problem, I've already filled in the shorthand notation for the alleles that are coming into the offspring from the mother's gamete. Of course, the father's gamete is always going to bring in a little b, a little e, and a little c, but we're not writing that down on all of these. And so I added up 2,000 offspring. The first thing you want to do is identify your parentals, and I guess I'll just highlight these. Let's see, and that's another parental here. And then your DCOs, maybe a different color, and DCOs here. So your parentals are the 665 and the 689. Your DCOs are 25 and 22. And using the method that we used in class, if you look at the 2 parental chromosomes, then you look at the 2 DCO chromosomes, you will notice that if you switch the B's in the DCOs, if you put this little b up here and put this big B down here, you will recreate your 2 parental chromosomes. So that means B has to be in the middle. So when we're working out our mother's genotype or our mother's layout, we're going to rewrite our mother's with a little e and a big B, little e, big B, little c, and then we'll have a big E, little b, and big C. And that would be your 2 mother's chromosomes. And you're going to want to then calculate your segment 1 crossovers. You're going to be looking for a little e with a little b, or a big E with a big B. And when you go through the data, what you'll see is that, and I'll highlight these. Remember, you're ignoring the C because C is not in segment 1. So the first one, this first one, that's a yes. So 22 is a yes. 95 is a yes. And then 203 is a no. 665 is a no. 689 is a no. 211 is a no. 90 is a yes because you got the little b and the little e, and then 25 is a yes. So you end up with 22 plus 95 plus 90 plus 25, and that will all be divided by the total of 2,000. All right, so that's your setup there, and you'll get a percentage. In my answer key, the percentage is going to be 11.6%. So it means there's 11.6 map units between any allele of gene E, and any allele of gene B on this chromosome. It's a guinea pig chromosome. Now, on the second segment, you're going to be looking for, now here we consider B and C, you're going to be looking for a big B with a big C, or a little b with a little c. Little c. And the numbers, go back to the data. Now here you have to ignore the E. So the first one, the 22, is a yes. The second one, 95, is a no. 203 is a yes. 665 is a no. 689 is a no. 211 is a yes. 90 is a no, and 25 is a yes. So you end up with, if you were keeping track, 22 plus 203 plus 211 plus 25. So you will always have the double crossover. The DCO numbers should appear in the calculation for segment 1, and they should reappear in the calculation for segment 2. And that's because they represent a crossover in segment 1 and a crossover in segment 2. That's why they're double crossovers. So you end up with a percent of 23.05%, and that means there's 23.05 map units between B and C. So then you would draw your map, and when you draw the map, you can put, it doesn't matter what you put in terms of the letters. It's going to be hard to draw here with the computer, but you're going to put maybe an E, and then here I'm going to try to draw it to scale. Any letter E, any letter B, and then over here maybe any letter C. And then, oops, what happened? And then the distance between E and B, you'll put 11.6 map units and put arrows here. And then the distance between B and C, 23.05 map units. You can see on the answer key how that looks. Now, what is the allele configuration of the female parent? Remember, this is our female parent's genotype. We have E and C are in cis. That means the recessive alleles are on the same one. Oops. It keeps capitalizing that for me. Thank you, Microsoft Word, but no. E and C are in cis, or in a cis configuration. Both are in trans to B. So that would be your statement. For the coefficient of coincidence, you're going to multiply. First, you have to figure out the expected DCOs. So expected DCOs, I'm just going to write it that way, is the recombination frequency for segment 1 times the recombination frequency for segment 2. And remember, I recommend you use the decimal numbers for this. And times 2,000, which is the total. And that will get you 53.476. So your coefficient of coincidence is your observed. Your observed is from the data, so you'll say 25 and 22, so 47. So 47 divided by the expected 53.476. So remember, your expected is what you just calculated. Your observed comes from your data chart. And that will give you a CFC of 87.9%. or 0.879, and then your interference is 1 minus that number, so your interference is 0.121, because that's 1 minus the CFC, which is 0.879. So that's how you do problem 1.